Hello everyone, again this is Professor Keen, and this is the second part of my introductory lecture on Chapter 20 of A Student's Guide Through the Great Physics Text, specifically the lab exercise we're going to be doing this week. So what I'm going to do is I'm going to right away go over, get rid of the webcam, and talk about Newton's laws of motion. So last time I talked about Newton's first law, the principle of inertia. The second law, so I'll just remind you, the first law is the principle of inertia. The second law that I developed is that when a force acts on something, it changes its momentum. So delta P, the change in momentum, is equal to the force times the time during which the force acts. So this is the change in momentum. It's caused by a force acting on it, and this is the time during which the force is applied. Okay. Now, some of you, by the way, might have remembered that Newton's second law is written in a slightly different way. It's written as force equals mass times acceleration. And if you remember it this way, then you're right. This is another way of writing this law, although this one is a bit more general. The way that we are writing it up here is a bit more general. I'm going to talk about the relationship between these two in a later lecture, but just at this point, we're going to use Newton's second law in this form because it's actually a little bit more general way of thinking about it. Okay, so Newton's second law says that when you have an object that experiences a force, its momentum changes, and its momentum change can be given by this formula. There's one other aspect of this that we did not talk about last time, and it is that this not only gives you a way of computing the change in momentum, but he also mentions that the direction of the momentum change is in the direction of the force. So the direction, and this is an important point, the direction of the momentum change, the direction of delta P, is in the direction of he calls it the impressed force. We'll just call it the force. Okay, so for example, this is going to be a really important point, especially for this lab. If you have an object that has a momentum that's initially going in this direction, so I'm kind of denoting this by an arrow. You might think of this arrow, the length of the arrow, denoting how big the momentum is, like 10 kilograms meters per second or something like that. And the direction as the direction it's going, maybe this is headed due east. If I apply a downward force, let's say a south force, that means that the change in momentum is in the downward direction. So let's suppose that the force is this way. That means the change in momentum is in that direction. So delta P is in the direction of the force. Okay? What that means is it's going to give us a way of figuring out the final momentum. And the way we can do this, if the initial momentum is that way, the change in momentum is this way, then we know that the final momentum is going to be in this direction. There's sort of this construction method, this geometrical construction like this. So delta P tells you if you had this going sideways and you have a change of momentum downward, then afterwards the new momentum is going to be kind of sideways but a little bit down as well. Okay, this is going to be an important point. That's a kind of a complicated case. There are simpler cases that we could do. Like for example, if we have an initial momentum in this direction and we apply a force behind it, so just think about the hockey puck sliding to the right. If we apply a force behind it by hitting the back of the puck with the hockey stick, the change in momentum is in the direction of the force we're applying. And so as a result, the final momentum is going to be in the same direction as the initial momentum, but it's going to be a little bit longer. That is, its momentum is going to increase. Or we could have an initial momentum in this direction right here, if the initial momentum is that way, and we apply a force to the front of the hockey puck, it's going to slow it down. That means its change in momentum is in this direction. It's got a backwards change in momentum. And so as a result, the final momentum is going to be drawn like this. It's going to be in the same direction as before, but it's going to be a little bit shorter, a smaller momentum than it was before. So this is the case of the hockey puck speeding up. Its momentum increases. This is the case of the hockey puck slowing down due to a force applied to the front of it. And this would be the case of the hockey puck changing direction. Okay? So I'll leave that as my initial description of Newton's second law. Let me say something more this time about Newton's third law. Newton's third law is the simplest to say, but the hardest to understand. Okay, so I'll say it first. For every force, there is an equal and opposite force. Or as Newton says it, for every action, there's an equal and opposite reaction. He uses the term action and force interchangeably. Okay, now, what is meant by this? Well, the example he gives is that if your finger, let's say, is pushing on a stone, so I'm going to draw a finger. Okay, so here's your finger. So that's kind of a bad thumb. Okay, and here's your finger right here. If your finger is pushing on a stone, so there's a stone, your finger pushes on a stone, then the stone pushes back on your finger. Okay, so if you are pushing, if you kind of represent your finger by like a dot and the stone by a dot, we'll talk more about this later, but there's kind of a simplification. This represents your finger schematically, and this represents the stone. If your finger pushes on the stone with a force in that direction, then what happens is the stone pushes back on your finger with the exact same force, but in the opposite direction. Okay, this doesn't just apply to fingers and stones. This applies to any two objects that are interacting. You need two interacting objects. In this case, the object are your finger and the stone. But you might think of, if you push on your brother with a certain force, your brother is going to push back on you. If you have a rope and you're pulling on the wall, the rope is pulling on the wall and the wall is pulling on the rope. These don't actually even have to be in contact. It could be two magnets. For example, if the north pole of magnet A is pushing on the north pole of magnet B, then the north pole of magnet B is pushing on the north pole of magnet A. Okay? So this is going to be critical in understanding action-reaction pairs in the lab. Okay? So, and the nice thing to keep in mind is you can always figure out an action-reaction pair by simply changing the object, the subject and the direct object in a sentence. So, for example, you can just do this grammatically, basically. Let me get rid of these things to get these out of the way. So, if you say your finger pushes a stone, okay, so this is in the nominative case. This is the subject of the sentence. And this is in the accusative case, you might say, if you study Latin. Otherwise, you'd say it's a direct object in English. Your finger pushes the stone, and how do you figure out the opposite force? Well, the stone pushes your finger. You're literally just exchanging the subject and the direct object in these two sentences. So these two forces are, this might be called force 1, is your finger pushing on the stone, and force 2 is the stone pushing on your finger. So your finger pushes the stone, that's force 1, and the stone pushes your finger, F2, and what Newton's second law is that F1 is equal to F2 in magnitude or size. They're in opposite directions, but their sizes are the same. And you can literally do this just grammatically by exchanging the subject and the direct object in these sentences. Okay? All right, so that is a brief introduction to Newton's 3 laws of motion. Let me stop there, and now I will introduce the lab in the next lecture.